So we will talk about 4 scaling strategies or techniques: the min-max scaler, standard scaler, robust scaler, and the normalizer. So first, the min-max scaler. So this is the formula. Xi prime is the processed transformed value, and is equal to xi minus the mean of x divided by the range of x. In this formula, x is a vector. So let me make it clear. Use different color. So this x is a vector. For example, we have n observations. Okay, this is a vector. And to min-max scale any observation in this vector. Okay? So xi prime. So you minus the mean of it and divide it by max minus the mean. Okay? Basically the range. The range of it. So let's study the range of the transformed data x prime. So consider 2 extreme cases. If xi is equal to the minimum of x, then what happens? Xi prime will be equal to 0 because the numerator will become 0, right? And this is one case. Another case is another extreme case. Xi is equal to maximum of x. Then you see the numerator will become max of x minus mean of x, right? Then xi prime will equal to 1. The numerator and denominator are equal. So the transformed data value xi prime will be equal to 1. So these are the 2 extreme values. And in normal cases, xr are in between min x and max x. So consequently, the transformed value xi prime must be in this range, okay? From 0 to 1 inclusive, right? So this is called a min-max transformer. After you transform the data, the vector, all of the values are between 0 and 1. If it's a one-dimensional data set, right, then all of the values are in this range. Okay. If it is 2-dimensional, then the transformed values will be within a unique square. Suppose there are 2 features variables, for example. Then all of the transformed values will be within this unit square. So it's quite restricted, okay, in a very small region. Right? So this is min-max. The next scalar, let's take a look at an example. So we load the Titanic data set again, right? And now we'll focus on the age variable. Age is numeric, right? Then let's use the min-max scalar to rescale the feature age. Okay, so first, load the submodule called preprocessing from Scikit-Learn. Okay. And then we first create a scalar, or you can say we instantiate a scalar. Instantiating means create some method or object with some parameters specified. So let's create a scalar. Use the min-max scalar function and specify the range. Feature range is 0, 1. So I believe this is also the default range, but you definitely can can transform the data into different, within different ranges. For example, you can let it be between 1 and 2, or -1 to 1. Okay? You just need to change these two values. All right, so this is a scalar with some parameters. Then we can call the fit transform method to transform the age column and save the result in scaled age. And then let's run it and extract the first three values in the transformed age column. So these are the three values. So they are all within the range between 0 and 1 in this interval, right? So notice that I use 2 layers of square brackets here because I want to make it a column vector. Okay, if you use single bracket, I think you will get a row vector. Anyway, this is an example of using min-max scalar to scale your data. And notice that we use fit transform, but actually there are 2 options to scale a feature. One way is to first call the fit method to calculate the min and max values of the feature, and then use the transform method to rescale the method and rescale the feature. So basically, you can do it separately, fit and transform, or directly call fit transform. Mathematically, there is no difference. However, when we talk about machine learning, you will see that we will prefer the first option. Okay? That is because usually in machine learning, before we even start training the data, we split the data to 2 parts: a training data set and a test data set. Right? So usually when we pre-process data, we will apply the fit method on the training set and calculate necessary statistics. If we use min-max scalar, we will calculate the mean and max for each column, for example, and save it. And then we call the transform method to apply it on the training set, and also use the same scalar with the same mean and max that are calculated from using the training set to transform the test set. That is because, remember, our model will be trained using the training set. So consequently, our test set is assumed to be in the same population with the training set, and the model is fitted using the training set. So it will be better to use the min and max, the parameters that calculated from the training set, to scale our test set. Okay, so that the test observations are assumed to be from the same population of the training set. So at that time, it will be quite different. Right? For now, it doesn't matter, okay, because we are not there yet. We're just talking about scaling. So for now, we can just directly call fit transform. And this fit method will calculate some parameters. It really depends on the scalar or the model you are using. If we use, for example, the next scalar, the standardizer, okay, then the fit method will calculate the mean and standard deviation of each column. Okay? So it really depends on which scalar, which model we are using. The fit part will calculate some parameters, okay? Statistics. Okay? And the second scalar is standardizer. So it's similar to calculating a z-score. Okay? Again, so this x bar is the mean of the column, okay, the column vector x, and s is the standard deviation of the vector. So calculated xi. So after the transformation, then the mean of x prime will be 0, right? And the standard deviation, the variance of x prime will be 1. So it's kind of like standardization process. So this is called standardizing. So let's transform age using the standard scalar. So first, let's instantiate it. I call it scalar2. And notice that we just use default parameters, and call the fit transform function method and apply it on the age column. And then we pull out the first three values. So notice that after we standardize the values are not bounded. However, the mean and the standard deviation are fixed. The mean is equal to 0, the standard deviation is equal to 1. But there is no lower bound and upper bound for the transformed values. Okay? So this is standardization. And then after we do that, let's test if the mean of the transformed data, standardized data, is indeed 0. If we just directly apply the mean function, you will get a missing value. So that's because, remember, age has a lot of missing values. Okay, and after you transform the data, there are still a lot of missing values. And the mean function will not ignore missing values automatically. To fix that, we can use this function instead, NaN mean. So this function will automatically ignore missing values and calculate the mean for all non-missing values. So see, the mean of the standardized age column is equal to this. Not exactly 0, but very close to 0. So this is negative 1.88 times 10 to the negative 17. So this means 10 to the negative 17. Okay, so 1.88 times. So it's very close to 0. Okay? So it's not exactly 0 because it is due to some rounding error in the calculation process. Okay? So in concept, after we standardize the data, the mean of the column should be 0. Okay? We can also verify that the standard deviation is 1. Standard deviation is good. It's exactly 1. So this is the second scalar, standard scalar. So what's the difference? The min max scale values are between 0 and 1, so they are bounded. So basically, after you use the min max scalar to process your data, the mean and the max of each column are fixed. Okay, mean is 0, max is 1. Right? So two statistics or two parameters are fixed. And if you standardize your value, then the mean and standard deviation will be fixed. Okay? Mean is 0, standard deviation is 1. But minimum and maximum are not fixed. Okay? So standardization is more common to use for machine learning pre-processing. However, it really depends on the learning algorithm. For example, principal component analysis works better using standardization, right? PCA. So this is an unsupervised learning method. It prefers standardizing. But neural network likes min-max scale data more. Right? So it really depends on the model that will use the data. All right. Then sometimes if your data is quite normal, namely is roughly speaking symmetric, or at least is unimodal and is not severely skewed, then the mean and standard deviation are good quantities to measure the center and the spread of data, right? So if the data is relatively symmetric and not skewed, then mean and standard deviation are good measurements of the center and the spread of data. However, if your data is very skewed, then mean is highly influenced by extreme values, outliers, and also standard deviation is also, because both of them will use all of the observations in your data set, all of the values in each column. So they are highly influenced. In this case, if your data is very skewed, it's better to use robust measurements of center and the spread. The robust measure of center is the median. It will measure the true center. And the robust measure of spread will be interquartile range, which is the third quartile minus the first quartile, right? Because quartiles are not influenced by outliers, right? So this is the 75th percentile, this is the 25th percentile. So there is a scalar called robust scalar, the robust scalar. So instead of subtracting mean from each observation, we subtract the median from it. Right? So use the median to measure the center and divide the whole thing, the difference by IQR, interquartile range. So this is called the robust scalar. Right? We use IQR to scale the data, use mean to center the data. Okay? So consequently, this is more robust to outliers. So if your data is not very normal, then use the robust scalar. Okay. So let's see how to run it. So we first create a scalar, call it scalar 3, robust scalar. This is also in the pre-processing submodule in Scikit-Learn. Then fit transform age. Let's pull out the first 3 rows. And it's not bounded. Okay, it's not bounded, just like the standardizer. Okay, it's not bounded, but the median should be 0. Okay, the median should be 0 because you see in the formula we subtract the median from each observation. Consequently, the median should be 0. Okay, you see. And by the way, we should use this function NAN median because there are missing values in the processed data. So this is a robust scalar. The last one is a normalizer, normalizing observations. So far, the 3 scalars we talked about focus on columns. And notice that it in the fitting part, okay, it will calculate some statistics for each column. If we use min max, we calculate mean and max for each column. And for standardizer, we calculate mean and standard deviation, use them to scale the data. And for a robust scalar, we calculate the median and the interquartile range. Okay. So all of them are about a column. Okay, so it will calculate these statistics for each column individually. So focus on column, and then use these statistics to scale or process each column respectively, right? But normalizer is different because it will rescale. It will focus on rows. It will focus on rows. So it rescale the values on individual observations to have a unit norm. So instead of focusing on columns, it will focus on rows to make sure that the norm is equal to 1 after we process the data. So what is a norm? There are different types of norms. The most commonly used one is the Euclidean norm. It's defined in this way. Square root of x1 squared plus x2 squared all the way to xn squared. So here x is a vector again. So let's clearly define it. So And the norm is the square root of sum of squares of all of the values. Right. So this is an L2 norm, called L2 norm. Now how to process transformer data? It will divide each observation by its row norm, and then call it x prime. So let's try to understand the scheme and why after the transformation, the norm of each row will become 1. Let's go back to the previous slide. I created an empty slide for derivation purpose. So let's clearly define everything. Okay. X is the features matrix. Right. Suppose there are P columns. And suppose we have n observations in our data set. So this is a feature matrix, a regular feature matrix with n observations and P columns. Right? Then normalizing will focus on each row. Right? Let's calculate the transform norm. Right? So for example, x2, let's focus on the second row. x2j will be equal to x2j divided by the norm of x2, right? Where the norm of x2 is square root of x21 square all the way to x2p square. Okay. All right. We do the same thing for each j. J is from 1 to p. We do the same thing for each number on the second row. Okay. Then after the transformation, let's verify that the norm of x prime, x2j primes will be equal to 1 after transformation. Okay. So x2 prime norm, okay, by definition is equal to x. So then you add all the numerators together. So it's 1. All right. So we have proof that after transformation, the norm of each row will become 1. It will become 1. Okay, it's very clear, right? And then, for example, if you have a 2-dimensional features matrix, right? 2-dimensional features matrix. Consider the transformer data x1 square, x2, x1, x2 prime, okay, after the transformation. After transformation, okay, let's consider a particular point. Then measure the distance between the point to the origin and call it the radius, right? The radius. So by definition, is equal to x1 square, square root of x1 square plus x2 square prime square. Okay. And we know that after the transformation, the norm is equal to 1. Okay, so this is exactly the norm of this vector, okay, or point, okay, is equal to 1. So consequently, after you normalize your data, all of the transformed observations or data points will be on a unit circle. They might be positive or negative, but the distance, which is the norm, right, L2 norm, is always equal to 1. So if you have 2-dimensional data, after you transform the data, they will be on a unit circle. All right, sorry about that. My derivation is a little bit how to say, bumpy. Sorry. All right. So this is normalizing. So the key point is we are transforming data along the rows. Okay? And after the transformation, the norm of each row is 1. Right? That's it. Okay, that's the key point. Let's see how to do it. So first import the normalizer from preprocessing. So now we will create a smaller features matrix with only 2 columns. And we first create the normalizer. Choose norm to be L2, which means we are using the Euclidean norm. Okay? Euclidean norm. Call it normalizer 2, and then directly transform the features matrix. Okay? So see, this is the transformed features. You can verify that you square the first term and square the second term and add them up, it should be equal to 1. And take square root, it should be equal to 1. Okay? You can verify it easily. And alternatively, you can use L1 norm. Okay? So L1 norm is the sum of the absolute value of each values in a vector. Okay? So to do it in Python, we can just specify this argument norm equals L1. Okay? Call it normalizer 1 and transform the features. Okay? Then after transformation, the sum of the absolute value of the values in each vector is equal to 1. So now this is very obvious. 0.5 plus 0.5 is 1. All of them are positive anyway. Originally they were positive, so that's why they are also all positive. The sum of them is always equal to 1. Right? All right, so this is another way to normalize your data using one norm. So L1 norm is also called Manhattan norm. So this is a summary of all the rescaling strategies. Standardized scalar. So this is for, so after we standardize that, we ensure that for each feature, the mean is 0, the variance is 1. And the robust scalar works similar to the standard scalar. It ensures the statistical properties for each feature that guarantee that they are on the same scale. However, robust scalar uses a median and interquartile range inside of standard deviation. And min-max, after the transformation, then the mean will be 0, the maximum is 1. And the normalizer will ensure that the norm of each row will be equal to 1. Let's take a look at this diagram, this plot, to sort of compare these 4 scalars. So this is original data, okay. 2-dimensional, x1 and x2, only 2-dimensional. And x1 is between 10 and 15 originally, and x2 is between 0 and 10. Right? So in this kind of rectangular region. Right? And we color them using 2 colors, red and blue, so that we can visualize the change of these 2 groups of observations in the transformed data set, right? So that you can have a better understanding of the effect of transformation. So standard scalar, after you standardize it minus the mean divided by standard deviation, so the data will be kind of like within a circle, right? Like a cloud, circle cloud, right? But there is no boundary, right? There's no specific boundary. And robust is kind of similar to standard scalar, but it's more like somehow like a diamond shaped region, right? But still not bounded actually. Right? And min-max, as we have I have demonstrated if you use min-max scalar for two-dimensional data, after the transformation, they will be within this unit square. And lastly, normalizer. After we normalize the data, all of the transformed observations will be on a unit circle. And the reason that for our data is in this region is because both x and y are positive. X1 and x2 are positive, right? So that's why after we transform them, they are also positive in this region. But they are on this unit circle.